So, yeah, last class we discussed about Newton's method. Okay, Newton's method in the sense you solved one of the problems and actually felt how Newton's method can be used to solve optimization problems. Okay, but I would warn you that you learned only one-dimensional Newton-Raphson method. Till now, you have not seen multidimensional Newton-Raphson method to solve or optimize multidimensional objective functions. Okay, yeah. So we'll see what is we'll see some examples. We'll see some examples known as multidimensional unconstrained optimization. What are like we'll see some techniques through and some examples, and yeah, through that we'll cover. You'll gain some intuition about why for multidimension we are using like this. Why for multidimension we are using this, that, and all. Okay. So the class will begin just with some examples. So multidimensional optimization. Clear, right? It's clear. Okay. So what is meant by multidimensional? So yes, you have like a function which takes a vector of inputs, that is x bar. If I write x bar, it means that it has more than one input. It has more than one input, like x1, x2, x3 till xn, n set of inputs. And that is being, when you apply f, which takes such n inputs and gives you an output y. So as usual, x bar belongs to Rn, that is set of real numbers in n dimensions, Rn, okay? And what is the function f? It takes a vector in n dimensions, Rn, and what it gives you? A real number. Okay, it takes many real number inputs in n dimensions and gives you one output. The same thing you can think of this neural network. It takes a lot of input values, x1, x2, x3, depending on the weights, and then the sigma does the operation and spits out one value. So this is like this function f takes m plus one set of variables and does some operation and gives you one red arrow you see. It is the output, one output, real number. The same thing here I am saying. So y equals to f of x bar. It takes n inputs, okay? X bar belongs to Rn, and then when you apply the function to that n sets of variables, it will give you real number. Okay, so that's fine. That's fine. So especially this x bar you can think of as this x1, x2, so on till xn, and usually any vector we write in column form. Any vector we write in column form. Why? Because it is easy to multiply with any matrix. Any matrix you take, it is very easy to multiply with a column vector. Okay. So therefore we take a transpose. That's how we denote things. If you don't want, you can always write it in row vector, but that's how we denote things. Okay. Fine. So what is the necessary condition for local minima? What is the necessary condition for local minima? So if you know about, just use your mind, like just use your thoughts or intuition, boil it down to always one dimension. For one dimension, you know that you need a derivative. So when you come to higher dimension, what is the generalization of the derivative? When you take one dimension, derivative you take. When you come to higher dimension, what you do? Yes, gradient, simple enough, because that contains the information regarding partial derivative. Simple enough. So this is the necessary condition. So necessary condition for local minima. Necessary condition for local minima is, so grad f, that is gradient of f, at some point, you will have minimization at some point. Okay. So at some x equal to x star equals to 0. So you say that at x equals to x star, the function f has attained a local minima. Okay, and therefore grad f at that point x equals to x star is 0. Fine. So yeah. So this, what is x? What is x? In computer language, many of you have learned coding. So in computer language, you take something, a function, or function always takes an argument and gives an output, or a function takes an input, gives an output. So in optimization, instead of saying it as input, we use a different word, that is argument. That is an argument. Okay, like same optimize this function. We never say optimize this function. We say optimize this objective function. Optimize this objective function. Okay? So therefore, similarly, what is this x star? X star is the argmin. We say it is the argmin, okay, of fx. Okay, it's the argmin argument where minimum of fx is achieved. So break this. This might be tricky. Break this into two things. So x star is the argument where minimization of the function is achieved. Understood? Okay, so therefore that's the way of writing this argmin of fx. Okay, what is x? What is x? X bar is any vector on Rn. X star is any vector or on Rn. Okay. Yeah. But this is the necessary condition. What is the sufficient condition? What is the sufficient condition? I already told this in last class. What is the sufficient condition? Hmm? What is sufficient condition? You know about necessary condition, but what is the sufficient condition? Go again to one dimension. Go again to one dimension. What you do, f prime of x, when you set to 0, derivative when you set to 0, you don't know whether it can be a maxima or a minima. To understand more that if it is a maxima, what you do, take the double derivative. Take the double derivative. If it is less than 0, double derivative is less than 0, you say it is maxima. If it is greater than 0, double derivative is greater than 0, you say it to be minima. Similarly, here, when you go to higher dimension, multidimensional, the double derivative is, what shape does the double derivative take place? Already told in last class. Hmm? What shape does the double derivative take place in high dimension? Not exactly double derivative, but second order derivative, you can say. No, you have to, yeah, this is not good. You have to see. You have to read a bit. What you do? You took the gradient. Gradient is like a derivative. If you want a second order derivative, what you do? Apply gradient again. If you apply gradient again, what it becomes? Huh? Yes. So think like that. You have to train your mind to think. This much deep and very smooth, and no one will tell. Okay. So try to think, make some generalization. So what is the necessary and sufficient condition? So necessary and sufficient condition. Necessary and sufficient condition for minima, okay, is first of all grad f at x equals to x star will be 0. That's fine. Second is del to f or the Hessian is positive definite. Is positive definite. Sorry, grad f at some point, it should, yeah, always remember this. You evaluate a derivative at some point. Similarly, you evaluate the gradient at some point. You evaluate the second order derivative at some point. Okay. So therefore, Hessian grad to f is positive definite is okay, correct, but not correct entirely. You have to substitute x equals to x star. At that point, it should be positive definite. Okay. So grad to f at x equals to x star is positive definite. What does it mean? What does it mean to have to say it is positive definite? All eigenvalues are. Yeah. So you're getting confused. There is something known as positive semi-definite and something known as positive definite. Yes. Positive definite is greater than zero. Positive semi-definite is greater than equal to zero. Okay. So if it is positive definite, all eigenvalues are positive. All eigenvalues, all lambdas, you can say, all lambdas are positive. What's the other way of saying this? What's the other way of saying this? What's the other way of saying this? You can say that y transpose del 2f y is always greater than 0 for any y in Rn. I hope that's correct. Yes, that's the meaning of positive definiteness. If you want semi-definiteness, only add 1 equal to sign to 0. That's it. Okay, fine. So this is the necessary and sufficient conditions. Of course, you should tell me that is it true? Can y belongs to all Rn? You should think. Don't believe whatever I read. Question. Y belongs to Rn. Why is it is correct? Correct. Sure. Why? I can give you a candidate when it fails. This statement is not true. This statement, something is wrong in this statement. What is wrong? Anyone? What is wrong in this statement? When it can fail. Hmm? When it is less than equal to 0. When it fails. Simple aptitude. Simple aptitude. When it fails. It will fail when it equals to 0. When it can equal to 0. To write all y belongs to Rn. Can 0 also belong to Rn? Yes. So that means we are including y equal to 0 also. When you include y equal to 0, 0 multiplied by this multiplied by this equal to 0, that will fail. It will fail. It will not be greater than 0. So therefore, you have to make one additional condition that y is not equal to the 0 vector. Y can be any vector in Rn, but it cannot be the 0 vector because that's where it fails. Yeah, you have to look into like this. Okay. So many things will appear correct to you, but might not be correct. This is one such example. Okay. So try to understand the situation, try to question whether it is true. Can I find an odd man out which can break this condition? Okay. Fine. Okay. So I hope you know about the structure of Hessian, you know the structure of gradient. Okay. So when you have n equals to 2, when you have n equals to 2, that means you have a function in 2 dimensions. You have a function in 2 dimensions, that is x and y. Then it becomes something very nice. It becomes something very nice. And actually, before going into this n dimensions, a scientist named Sylvester, okay, they found that they did this condition for n equal to 2. For n equals to 1, everyone knows. Solve f prime equal to 0. Solve the double derivative less than 0 or greater than 0. Okay. But for n equals to 2, what you do? for n equals to 2. For n equals to 2, we don't know. For n equals to 2, Sylvester found the condition. After n equals to 2 is formulated, then people went to high dimension. That's how the theory was developed. Okay, fine. For n equals to 2, you will see that del 2f is positive definite. Del 2f is positive definite if anyone, del 2f is positive definite. That means huh, that is known. That I will write second time again. Del 2f is positive definite. That means determinant of del 2f will be greater than 0 because all eigenvalues are positive, isn't it? All eigenvalues are positive. And and something more is there. Del 2f is positive definite if determinant of del 2f is greater than 0, and also the partial derivative with respect to the first variable is greater than 0. Okay, this is the condition. This is the condition. Like, if you want necessary and sufficient condition for a local minima, okay, you can understand now why it is greater than 0. Why it is greater than 0? Okay, because we are searching for a local minima. We are searching for a local minima. Okay, for a local minima, if you are in 2 dimensions, note that this won't work in higher dimension. This is known as Sylvester criterion. This is known as the Sylvester criterion. This is known as Sylvester criterion. Okay, and the idea is del 2f is positive definite if determinant of grad 2f is greater than 0 and the second order partial derivative with respect to the first variable is greater than 0. Fine. We'll see some example. Note that this works only for the 2 dimensions. It won't work for higher dimension. Okay. We'll see one example. The best way is to see an example. Take this function. Like, we want to minimize f of x comma y. It's a 2-dimensional function, that is x square plus 2y square minus 2xy minus 2x. Suppose we want to minimize this. Okay. So as usual, what you will have like, it is just saying that if you want to form above, like minimize f of x, if you want to the ideal way is solve minimize of f of x, where x vector is xy column vector. Okay, fine. So how we can use the Sylvester criterion? Our aim is to find x star vector which is equals to some x star y star, such that this x star vector is the argument where the function is minimized, arg of min of f of x in R2. Okay, can you apply Sylvester criterion? What you will do, you will compute grad f, you will compute Hessian, you will check the determinant, you will check whether the first derivative is greater than 0. Can you try? Try and let me know. Okay. So what is gradient of f? How many variables are there? 2 variables. So gradient solves the partial derivative. It will have partial derivative. How many partial derivative it will have? With respect to x, with respect to y. So it will have dou f by dou x, dou f by dou y. That's it. So what is dou f by dou x? Y will be constant, so it will be 0 derivative. Come to this. So minus 2y. What will be this? Minus 2. Then with respect to y, what it will be? Yes, for x square it will be 0, because when you derivative with respect to y, treat x as constant. So x square, when you take the derivative of x square, it will be 0. So come to this derivative of with respect to y, 2y square. Apply power rule. 4y. Then minus 2xy. Here 2x will be treated constant. Take it outside. And y is just linear. So 1 minus 2x. Then this will be constant. So 0. So 0 minus 0. So 0 plus something. Okay. So this is the gradient. This you set. So what you get? This implies 2x minus 2y minus 2 equal to 0. 4y minus 2x equal to 0. So can you solve this simultaneous equation and tell me what are the values of x and y? X star y star is 2, 2. 2, 1, finish. But you don't know whether it is minima or maxima. What you do? Compute the second derivative. Second derivative here in 2 dimension is known as Hessian. That is grad 2f. That is grad 2f at x star y star, right? You have to solve what is grad 2f at x star y star. First of all, what is grad 2f? Grad 2f will look like, it will be a square matrix. Okay, it will be a square matrix. What is the order of that square matrix? 2 by 2. 2 by 2. Because you have two variables. 2 variables, 2 by 2. 3 variables, 3 by 3. N variables, n by n. No. So what should be the Hessian? This we write grad 2f or H. H for Hessian or grad 2f. How you will solve the Hessian? Hessian will be dou 2f by dou x2, then dou 2f, the mixed derivative, dou x, dou y, then dou 2f, dou x, dou y, dou 2f, dou y2. Okay. So can you tell me the value here? At that point, dou 2f by dou x2. So what you do, just take the derivative of this. Take the derivative of this quantity, right? So dou 2f by dou x2, what you will get? 2. Okay. Then dou 2f by dou xy means, that is, you have to take dou of dou f by dou y. What you get here? Yeah, 2 minus 2. Then dou 2f by dou x dou y. What you will get? Okay, check this. Dou by dou y of dou f by dou x. What you get? Same you are getting. Okay. And dou 2f by dou y2, what you are getting? 4. Okay. Now what you have to do? Apply the Sylvester criterion. What Sylvester criterion says? That the determinant of the Hessian should be greater than 0. Right? So what's the determinant here? This is the Hessian. So the Hessian or the del 2f at x star y star, you are getting as a square matrix 2 minus 2 minus 2 4, right? Fine. So can you compute the determinant of the Hessian or the determinant of del 2f? What is it? Multiply 2 into 4, this multiplied by this, minus this multiplied by this. So minus 2 into minus 2. What is it? 4. Is it greater than 0? Yes, greater than 0. So part of the Sylvester criterion is satisfied. Now we have to check the second condition, that is dou 2f by the first variable, partial derivative, second order partial derivative, is it greater than 0? So dou 2f by dou x, here the first variable is x. Is it greater than 0? Can you tell me what value you get? 2, right? Here you got it. This is the value here. Dou 2f by dou x2. This value you have got here, 2. This 2 is greater than 0. Okay. This 2 is greater than 0. Fine. Now can you tell that yes, the first condition, that is the determinant of the Hessian, is greater than 0. The second condition, that is the second order partial derivative of the first variable, is greater than 0. So therefore, we can say what? What we can say? We can say that the point x star y star equals to 2, 1 is a local minima. Is a local minima or f of x comma y. That is it. Believing me blindly. Why are you believing me blindly? If it is the minimum, it is the minimum. If you put this value into the function f of x star y star, it should give you a sense of minimum, right? What should be that value? Can you put those values and tell me what you get? F of 2 comma 1, right? What should be the value? Hmm? Anyone? Minus 2. Okay. So it gives you a sense that yes, it is a negative value. So it gives you a sense that yes, it is kind of decreasing. I suggest you to plot this function. To plot this function, we might be playing with this function much. Okay, this function is very nice because it will give you some sort of elliptical kind of structure. I suggest you plot this equal to like this function x square plus 2y square minus 2xy minus 2x equals to some constant. Try different value like equal to 0, equal to 2, equal to 0.5, equal to minus 2, and see how the shape looks like. Hmm? You can use Desmos for this or Python, whatever. Okay. So you saw how you can apply Sylvester criterion to solve this, to minimize this two-dimensional function. Okay. Now let us come to regression. Let us come to regression. We will use a problem in regression and apply Sylvester criterion. Okay. Be quick. Okay, be quick. I will give you the problem you have to compute. Hmm? Okay. We'll take one simple example, regression that you have data set x and y, very tiny data set of only three numbers like 1, 3, 6. Then you have 6, 10, 2. This is the regression problem. Why we are taking so less numbers? Just to understand this method. Just to understand this method. So that you can at least compute it by hand. Hmm? These are two numbers. And the idea is we are trying to fit using this regression line. The y cap equals to w naught plus w1 by x. Of course, w naught and w1 are the weights. W naught and w1 are the weights. You will see in this course, attention, if you keep patience throughout the course, you will see that regression, optimization, neural network are just interconnected. They're just interconnected. Okay. See, we are talking about regression, but suddenly why we wrote W naught and W1 weights? I could have written A plus B by X because W naught and W1 are kind of weights. So there is some connection I'm trying to make between regression and neural network. When you're trying to optimize a regression problem, okay, like to minimize the error or in fitting your data set through a curve, you are optimizing the error. So therefore, optimization comes to picture. So you see how and optimization in neural network you already know, reduce training error. So you can see how regression, optimization, and neural network are all threaded into each other, are all intertwined into each other. Okay, if suddenly you are solving a root finding problem, why? You need you need the error to be zero, right? Remember, you need the error to be zero. F of x minus the root should be less than epsilon. First semester, you always checked that. What is the error you are getting? Either in Gauss-Seidel, Newton-Raphson, bisection, wherever. So if you want to reduce that error, again, minimize that error, optimization comes. So root finding and optimization, again, root finding and optimization, root finding. Root finding and optimization are again interrelated. So you can see how these branches are interrelated and why are we studying all this. Okay. Hope you are getting an idea. So, okay, let us return to the problem. This fits the data. This curve fits the data. We want to check. We are interested to check if the cost function, that is, of course, the error in regression has a minimum. If it has a minimum, it is a good idea, right? It is a good idea that yes, my regression problem attains a minimum. That means this curve is a good fit for my data. I hope you are getting the idea. Okay. What is the cost function? What do I mean by this? This cost function is given to you. This cost function is represented by E, that is the error, as 1 by 3, because there are 3 data set numbers. 1 by 3 summation I equal to 1 to 3. What you do? Any variable, that is y minus the fitting curve, y minus y cap square. I hope you know why we take the square. Because if you don't take a square, maybe the plus and minus maybe cancel out and give you 0 error. At the same time, error might not be 0. Error might not be 0. I hope you get that. Those who are blank, why we put a square? I suggest go home and see why we put a square. Okay. So, anyone can tell me what this value is? 1 by 3 summation I equal to 1 to 3. Yeah, maybe you can solve it. But I suggest, I have written it down. I will write it down for you. But check whether this part I have done is correct or not. Is it correct? I am writing it, but you should check. It is not that simple enough number. You might check. Then there won't be a summation sign, right? Then there won't be a summation sign because I have written everything down. I suggest try to obtain this big expression yourself to convince yourself that I have done correctly or whatever you are doing is correct. Fine. Now our job is to see whether the function E, that is the cost function of this regression problem, attains a minimum. If it attains a minimum, then it is good because then you can claim that use this weight W0 and W1 and put them here, and that will be the best candidate to fit your data set. Do you agree? How many of you agree? Anyway, so okay, I will tell the problem again. You have this data set. The idea is someone tells you that yes, this curve can fit your data. But now the question is, what value of W0 and W1 will you take so that it fits the data nicely? What it means, the fits the data nicely. What is meant by this term? It means that your error will be less. In the sense, suppose these are the data set X and Y. Okay, and what you do is, suppose you want to draw this line. Is this line the good line? No, because the points are, you already know it is a nonlinear fashion, they are distributed. So these are the errors. Isn't it? From the actual line, these are the tiny errors. And that's exactly what we are representing by E. Fine. Now my question is, through optimization, you have to find what value of W0 and W1 minimizes the error or the cost function. If you find W0 and W1, just put it here and claim that this curve fits your data set nicely. That's it. Now, can you solve this optimization problem? How? How many variables this optimization problem has? What are those variables? This column, and who tell someone. Well, how many variables are there? How many variables are there? What are they? Huh? What are those variables? What are those variables? No, no. Yeah. These are the parameters, but that's what we are optimizing. So E is a function of W0 and W1. Our problem is to minimize E of W0, W. Yes, for cost function, these are the two variables, W0 and W1, and you want to minimize E. What value of W0 and W1 minimizes this? That's it. That's it. So this is a function of W0 and W1. Can you use Sylvester criterion? Can you use Sylvester criterion? Yes or no? Why? Yes, it's two dimensions. So you can use Sylvester criterion. So use. What you have to do? Compute grad E. Compute grad E. Set it to 0. Compute grad E. Set it to 0. First is compute grad E. Then second is set grad E to be 0. Yes. Then you will get some points W0 and W1. What you will do? That point might be maximum or minimum. To check whether it is local minimum, apply Sylvester criterion. That is determinant of grad 2 E should be greater than 0 and del 2 E by the first variable. What is the first variable here? W0. W0 2 should be greater than 0. This is the Sylvester criterion. After you do this step, you will know what W0 and W0 1 to be used so that it attains minimum. Okay, so I hope you computed this W0 and W1 for the regression problem. Now we are computing gradient, we are doing everything. The only question we have in mind is the only question we just 1 minute. Yeah, the only question we have in mind is the following. What is the importance of gradient? What you know so far about gradient? Given a function to you, just take the partial derivative. If it is two-dimensional, dou f by dou x, dou f by dou y, arrange it like a vector, and that is a gradient. I hope that's far you know about. But you know gradient is a vector. Gradient is a vector in two dimensions. In higher dimensions, is gradient a vector? In two dimension, it will be a vector because x comma y. In higher dimension, in 3 dimension, 4 dimension, will it be a vector? No, gradient. It will be a vector. I was waiting. Some of you will not tell vector. Okay, anyway, so this example is to show you gradient is so popular, and every class, without the term gradient, the class doesn't go forward. Okay. What is the importance of gradient and why the gradient is much important in optimization techniques? Okay, so let us come to one example here. I hope I suggest everyone to visualize this example. Visualize this example. This is about visualizing gradients. Visualizing gradients. Okay, consider this curve. Consider the two-dimensional curve f of xy, which we have taken before, the famous curve that is x square plus 2y square minus 2xy minus 2x equals to 7. If you put it equal to 7, it will be a curve. If you put equal to 3, it will be some other curve. Okay. Those who have opened their laptops, I suggest open Desmos. Open Desmos, I told in the first semester already, and type this curve, how it looks. Okay, we will differentiate this curve. With respect to x. Okay, that means I want to find what is dy by dx. Find what is dy by dx, and you already know if I find dy by dx, it will give me the slope, isn't it? Dy by dx gives me the slope. Yes. So differentiate this equation. Differentiate this. Differentiate. What you get? It's plus 4y dy by dx minus 2x dy by dx minus 2 equal to 0. I hope you opened Desmos and saw the curve. How many of you saw the curve? Can anyone show me the curve? Show me the curve. Yes, good. Exactly. It looks like a ellipse kind of structure. Yes. So therefore, I can draw this structure here. I hope it looks like this. Is it? It looks like this. Okay. Fine. This x and y, and this is what equation you have got. Can we collect dy by dx terms? What we'll get? 4y minus 2x. And what are the terms we have? Plus 2x minus. I hope this derivative is correct. Is this derivative correct? Just you have to take dy by dx of that, nothing else. See, our aim is, given this equation, we have to find what is dy by dx. To find dy by dx, we have to take the derivative with respect to x on both sides. If you take derivative of x square, you are getting 2x. 2y square, what you are getting? 4y dy by dx. So same thing you are getting here. And through this, we are computing what is dy by dx. Dy by dx equals to 2 minus 2x divided by 4y minus 2x, right? Is it correct? Or wrong it is? Huh? Yes, there is a mistake. Tell where it is a mistake. Huh? There should be minus 2y because dx x you derivative, it is 1. Actually, the same mistake last semester student also did. So yeah, that's the idea. So what you do, you have minus 2y here, isn't it? So you'll have plus 2y here. Am I correct? Is it correct now? 4. Yeah. So when you take derivative of this with respect to x, d by dx of minus 2xy, what you are getting? You apply the product rule. So you derivative with respect to x once. So that will result into minus 2y because dx by dx you will get. Okay. Then plus you derivative with respect to y keeping x constant, minus 2x dy by dx. So therefore dy by dx is this value here, this function, this ratio. Okay. Now what very nice we want to visualize this. Is at minus 1 comma 1. X equals to minus 1 and y equals to some 1. It is somewhere here. It is this point. We want to understand what is the value of dy by dx at minus 1 comma 1. What should it be? It should be the slope. Dy by dx at minus 1 comma 1 should represent the slope. Am I correct? Slope is nothing but the tangent. Am I correct? So if it is nothing but putting a tangent line. It is nothing but putting a tangent line. Understood, right? So dy by dx at minus 1 comma 1 is equal to what? What value? Can you tell? What's the value? Hmm? So you're getting 1. Dy by dx at minus 1 comma 1 is 1. That means it matches your intuition. It makes a 45-degree line. It makes a 45-degree line. I hope you agree to it. Is it clear? How many of you it is not clear? How many of you understood this? Then Saji understood. Understood. So what you understood? At x equals to minus 1 comma 1, what is the slope? 1. So it will make, the tangent will make a 45-degree line. Tan 45. Tan theta. So this is the slope. Slope is always equals to tan theta, right? Theta that the angle makes with x-axis. So theta equals to 45 degree. Tan 45 is 1. So this angle is 45 degree. Simple. Okay. So, but why we are learning about the slope? Why we are learning about the slope? The idea is, now can we calculate? This is the slope of the tangent. This is the slope of the tangent. Can we compute slope of the normal? Slope of the normal. Slope of the normal at minus 1 comma 1 is what? Slope of normal at minus 1 comma 1. What should be? Yes, because you know slope of the tangent and slope of the normal. I hope you remember class, your high school math a bit. And if they are m1, m2, slope of one line is m1, slope of another line is m2, and m1, m2 are perpendicular, okay, then m1, m2 equals to minus 1. Yes, isn't it? In high school, I hope you remember in high school. Okay. So therefore, if this slope is 1, what should be the slope of the normal? Minus 1. Okay, the slope of the normal should be minus 1. Fine. How the normal looks like? The normal should look perpendicular to the tangent. Perpendicular line. This is the perpendicular. So this is the tangent, whereas this is the normal. I hope it is okay. Now, 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 can we compute gradient of this? Now you know what is normal. How many of you understood what is the normal? What is normal? Hmm. Normal. Okay. I hope everyone knows about this normal now. Okay. Now I tell you why I told you about normal. I will tell you. Compute the gradient, and you will know why I talked about normal. I want to make a relationship between them. Compute the gradient of this f. What is the gradient of this f? That will be dou f by dou x, dou f by dou y, right? What should be the value here? Dou f by dou x gives us 2x minus 2y minus 2. What is dou f by dou y? 4y minus 2x, that much. Okay. Now I want to compute. I always told you we have to compute gradient at some point. Okay, we have to compute gradient at some point. So I want to compute gradient at -1, 1. At this point, what is the gradient? Because we always talk about gradient. We know gradient is a vector, but we never talk about what is the direction of gradient. Graphically, we never showed it to you. Okay, this is the part where you will know it. So compute gradient of f at -1, 1. What is the value? Just substitute 2 into -1 minus 2 into 1 minus 2, 4 into 1 minus 2 into -1. What's the value? Minus 6 and 6. Can I write this 6? Can I take outside and write -1, 1? What are you seeing? Can you see something here? Are you able to see something here? What is happening here? 6 times -1, 1. -1, 1 means it is this point vector. What is this -1, 1? What is -1, 1? If I want to plot -1, 1, what I do? Can I plot it with a magenta color? Can you agree that this is the vector -1, 1? Agree? Because x is -1, y is 1. Agree? Agree. So when you took gradient of f, it gave you -6, 6. 6, 6. So where it should lie? Maybe I can do with this green. So it will be 6 times the length of this. So it will be a bigger vector, maybe here. Are you agree? Do you agree to this? The green is the direction of the gradient. How many of you agree to this? Do you agree? How many of you agree here? Mr. Sandeep? This is just high school level things we are talking here. Slope, normal, direction. Simple enough. Here you are not understanding. Which part you are not understanding? Did you understand? This is the tangent you understood. Slope you understood. Normal. Normal is just the perpendicular to that tangent. Yes. Slope you got. Normal you got. So normal slope is already -1. Isn't it? Agree with it? Now that is the break there. That is the break there. Now after that, I told you compute the gradient. Gradient. How you compute gradient? Take the partial derivative. Dou f by dou x, dou f by dou y. This is the function. You got this value by partial derivative. Now we want to understand what is the value of the gradient at -1, 1. That is an example case. So at -1, 1, you just substitute this x, this y into this. So 2 into the x value is -1 here, and y value 2 into 1 -2 and so on. What value you are getting? -6, 6. Okay. Now we want to understand this is a vector. This gradient is a vector. We want to understand where this gradient is pointing to. Okay. -6, 6. You take 6 out common. Now where -1, 1 is, I drew it here. -1 is here. 1 is here. Right? So -1, 1. If I want to draw a vector, where it should lie? It should lie in this magenta line. This is the magenta line. Agree? Oh, this is -1, 1 vector. Can you plot the gradient vector? -6, 6. It will be -6, 6 will be where? Okay. Maybe I'm going one step ahead. -6 will lie here. 6 somewhere lie here. Okay. So can you plot it? So the gradient should point in this direction. From the origin, you always point. So this is the gradient direction here. Simple enough, isn't it? Simple enough. Agree? So Mr. Sandeep, you understood, no? Okay. Now, I could just finish it off with one sentence, but I am motivating you to discover by yourself. Those who have opened their laptop, I want to do this exercise and show it to your neighbor students. Now, this f of xy equal to 7, right? 7. Is it correct? I suggest you put it equal to 10. F of xy equal to 10 in a new color and plot it below. Now there can be two questions. If you equate it to 10 or what? Outside this black, isn't it? Agree. It will be smaller or bigger if you equate it. So which case it is? Bigger or smaller? How many of you are saying bigger? Agree. How you are saying bigger? Here looking from there. Yeah. Show it to your neighbor, show it to your backside people also. Backside also you show. Show. Adil. Mr. Chako. Mr. Adilson, look into Adil's. Oh, you have yours. Okay. So, what we discovered? This is the most important result of this semester. To be honest, this is the most important result of this semester. Okay. So, take it carefully. Don't believe me. What value you put? F of xy equal to 10. Can you put f of xy equal to 20? And put it in a new curve. Put f of xy equal to 30. Agree? So what are you understanding from this? That's my question. So when you put f of xy equals to, so what you observed, I will tell you. I will tell you what you have observed so far. If you put f of x comma y equal to some value k, first we put 7, then 10, then 11, then what you are getting here, suppose you are getting like this, isn't it? This is 7, this is 10, this is 11, isn't it? So when you increase the k value, it is increasing in size. That means the function value is increasing. The function value f of xy is increasing. Agree? How many of you agree to it? Yes, because see this line, f of x comma y equals to 7. So when you increase this 7 to 10, 20, 30 and all, f of xy is increasing. It is increasing in outward size, right? Like the universe is expanding, it is increasing that way. Yes. Now my question is the gradient pointing to the direction where it is increasing or opposite direction? See, the gradient is in this direction. Gradient is this direction and the function is also increasing in that direction. This statement, how many of you agree? Do you understand? Did you understand? No? No. What I am saying, this is the axis. Agree? This is the axis x comma y. This is your function curve, 7, 10, 11. So therefore you see this is increasing. What is the most maximum here? 11. What is the minimum here? 7. Yes. So the function is increasing in which direction? Radial direction. The function is increasing in this way. Function is increasing in this way. Don't you agree? It agrees, right? So therefore, I am telling you this only, like, what is the gradient here at -1, 1? at minus 1 comma 1, the gradient was along this line, isn't it? So the direction where the function is increased, the gradient also points along that direction. The gradient vector of the function points in that direction where the function is increasing. So the gradient points in a direction where the function value is increasing. This is the most important result of the semester. Most easiest to understand, but at the same time, most important to understand. Most easier to understand, most important also. Okay. So where the gradient should be, the gradient points in a direction where the function is increasing. So my next question to all of you is, if I want to minimize a function, where I should go? Hmm? Yes, exactly. If you want to minimize a function, you have to go negative to the gradient. Because in this direction, if it is increasing, okay, think of a road. Think of Kerala. I think you know in Kerala, the situation is like the roads are uphill most of the times. So if it is you are trying to go to uphill, okay, the bike is like the bicycle, you have to pedal more. But again, you want to come easier way without pedaling, you have to come direction, isn't it? That way, without any paddling, you just float it. Okay. So if you want to minimize the function, you have to go opposite to the direction of the gradient. Okay. But therefore, this is the gradient is something more special. The gradient is something more special in the sense that it not only gives you the direction where the function value is increasing, rather it is something strong. I will write it in red, that gradient points. This is the stronger statement in red, is always it points in the direction, where the function has steepest increase. Okay, where the function increases in the steepest direction, there the gradient points. Okay, the direction of the gradient is such direction that it points where your function increases in the steepest way. That's the speciality of gradient. That's the speciality of. And if you want to compute, so gradient is a vector. Now you know gradient is a vector. What is a vector? Go to class 12th. Go to class 12th. What is a vector? Vector is anything which has magnitude and direction. Direction, now we are paying respect to the direction part. Where we will go so that function increases, where we will go such that function decreases. But one thing we are keeping in dark is the magnitude. What about the magnitude of the gradient? Who will talk about it? What happens to the magnitude of the gradient? So magnitude of the gradient, or in many books, you might see it is referred to as strength of the gradient. Strength of the gradient. Strength of the gradient. So it indicates the magnitude indicates how quickly, how quickly the function value is changing. Okay, you understood that? So the direction of the gradient points where the function has steepest increase. Okay, you got that idea. That's the vector aspect, that's the direction aspect of gradient. Now I'm asking you, what is the magnitude aspect of gradient? If you compute the gradient and the magnitude you get, that magnitude will give you an idea of how quickly the value of the function is changing. Okay, how quickly the value of the function is changing. So these are the two things, two important aspects of the gradient, which is discussed by this very simple example over here. Okay? So I suggest if you keep on decreasing this value, like 3 will come here, 3 will come here, 2 will come here. Okay, so it will be. I suggest you play with that function a bit. Try different values. Okay, okay. Okay. Now my question is to you is this. I want to minimize f of x comma y, which is given above, that is that x square plus 2y square, that's full function. Okay. So how we can minimize this? My question is, so what you do in a practical case, if someone has given you one function, suppose in some deep learning aspect, you got one contour plot like x comma y, f of x comma y, you want, that is a training error. You want to minimize the training. How you will minimize the training error? How you will minimize the training error? You will plot it like you did the plot here for this example function. X comma y, maybe they will be the weights there, W0, W1. So you plot the contours. These are known as the contours. These are known as contours. This is for one function value 7. This is 110. For 11, you will get something like this. Okay. Then you know where the gradient points. Where the gradient point at minus 1 comma 1, it pointed somewhere in this direction. Okay. So in this direction, blue direction, the function is increasing. That's the steepest direction. If I want to meet f of xy, where I should go? I should move in the negative of gradient of f minus 1 comma 1 or x comma y, whatever. So if I move in this direction, it will give me the direction where the function is minimum. Where the function is minimum. Where the function is minimum. Okay. I hope it is okay to you. So if you want to minimize the function, which direction you have to go? Again, all should say this. Which direction should you go? Yeah, negative to the gradient or opposite to the direction. Yes, the same thing. So this idea, this simple visualization leads to a large family of optimization methods known as gradient descent. Okay, this motivated many of the scientists to formulate gradient descent methods. There are a lot of gradient descent methods. One is the regular classical gradient descent, GD, gradient descent. Okay. To improve it, something more, if you add stochastic noise to it, it is stochastic gradient descent. There is another version. If gradient descents are usually slow, therefore you want to accelerate that method, it is known as accelerated gradient descent. Okay. So there are many more methods like this. Okay. So we'll see those methods one by one. Okay. So yeah. Um, I suggest. Oh, I think I can show some Python codes, but I think those Python codes are for gradient descent. Did I show you any code related to Newton's method? I think we covered till this, right? maybe after learning a bit of gradient descent, we can come to the Python coding. Okay, because else you won't understand how this gradient descent works. Okay, how this gradient descent works. Once you understand the gradient descent, then we can look into all this aspect here in this coding. Okay, I think we have enough time for that. So I hope we'll cover that. And then I will show you something on Newton's method. How Newton's method, like I will show you why we learned convex function and non-convex function at the first place in the lecture, in the start of this course. Because I will show you Newton method works very nicely for convex functions, but at the same time, Newton's method kind of fails in case of non-convex functions. Okay, so therefore it is important to understand about convex functions and non-convex. We'll see this. So let me close this meeting and we'll start a new one.